I knew Dick Feynman quite well, and he was always kind of giving me a hard time about spending all this effort computing Feynman diagrams, because he was saying, like, Feynman diagrams are probably the stupidest way to compute what actually happens in quantum field theory, but he hasn't been able to figure out anything better. So then what happened in quantum field theory was Feynman diagrams, and the idea that you could kind of decompose the what happens inside. You could take the mathematical expression of what happens inside, and you could write it in terms of these collection of graphs that you could interpret as being the interaction of particles. So what we realized recently is that actually that isn't really the right interpretation of Feynman diagrams. I will have to say that as sort of a fun historical footnote, I knew Dick Feynman quite well, and he was always kind of giving me a hard time about spending all this effort computing Feynman diagrams, because he was saying, like, Feynman diagrams are probably the stupidest way to compute what actually happens in quantum field theory, but he hasn't been able to figure out anything better. But in any case, the question is, what really are these Feynman diagrams representing? And I think what we realized is that the lines in Feynman diagrams, that this is a particle, this is an electron, whatever else, those are actually causal connection edges. What's really happening, what a Feynman diagram really represents, is a collection of causal relationships between interaction events. You have some vertex in the Feynman diagram, you have some line, a propagator, that goes to some other vertex. In a sense, what's being done is particles in that case are really acting as, in some sense, the carriers of pure motion. They're acting as carriers of causality. They are sort of making a causal connection between this interaction event and that interaction event. And so that lets one sort of start thinking about sort of what's underneath Feynman diagrams. What really are they? They're really causal diagrams. And you can start saying, well, if I have this multi-way graph, actually a multi-way causal graph that shows me the causal connections between all these updating events, that multi-way causal graph is really the sort of entangled collection of a bunch of Feynman diagrams. And so you can start making sort of a toy version of Feynman diagrams. I haven't done this yet. It's still in motion right now, to make sort of a toy version of Feynman diagrams that correspond to sort of this way of mapping causal relationships, where the big thing, the whole enchilada, so to speak, is a multi-way causal graph. That's kind of the sum of all Feynman diagrams, is this multi-way causal graph. But when we're thinking about it in terms of quantum field theory, we're thinking about it, decomposing it in terms of this sequence of diagrams. So then what you realize is, once there are loops in those diagrams, you have all sorts of infinities, just like you do in quantum field theory. Their details are a bit different, but it's the same, seems to be the same idea. You start to have to think about ideas like renormalization, and you start to think about, well, there are all kinds of fun concepts that are not properly worked out, like the kind of notion of subtime, where you're kind of going through these causal loops that an observer, that no observer will ever detect. The observer is seeing only the effect of an infinite number of these kind of subtime loops, and it's sort of a renormalization type story that you're sort of extracting only the things that are observable beyond the things that sort of always happen, and therefore you sort of convolve into the kind of the fundamental nature of the particles or whatever you're looking at. So in any case, that's hasn't yet been worked out, but this is kind of another kind of attempt to see. Actually, let me make a general philosophical point. So in the history of the physics project, I've kept on thinking, we need to sort of build up the structure of things in kind of the way they've been built up in traditional physics. If we want to understand energy, we need to know what particles are, because particles are the carriers of energy and so on. Then we realize that's actually not true. There's a more foundational thing that is energy. This flux of causal edges through space-like hypersurfaces that is energy, or momentum is flux of causal edges through time-like hypersurfaces. Those are the things that are fundamentally energy momentum. But then it's like, well, particles can be carriers of those things. Well, yes, they can. Particles can be bundles of causal edges, but you don't actually have to think about that in terms of thinking about these fundamental concepts of energy momentum. And so similarly, when it comes to quantum field theory, and you're thinking about computing S matrices, computing correlation functions, things like that. You might have thought that you need to actually understand sort of mechanically what particles are and so on to be able to start working that out. But then what we've realized is, no, actually you don't. There's a lower level to these things that doesn't go through sort of the traditional physical intuition of, oh, and then there are particles and they interact and so on. So that's been sort of a continual learning that you can get to the answer without going through sort of the steps that you thought you'd have to go through. I mean, it's kind of like in a somewhat different area, although it might be more related than you expect, in machine learning, where you sort of imagined if you were doing like speech to text, oh, we have to make up phonemes, we have to do silence detection, we have to do this, that, and the other. Well, actually, no, you can go all the way from the speech to the text just by this one kind of uniform concept of neural nets. And I think the same is going to be true more often than we expect with the physics project. And that's been a thing that sort of, in a sense, held one up, that one's trying to find the phonemes, so to speak, and one doesn't really need to do that. You don't really need to find all those things where you say, well, let me actually find this particular characteristic of this particular particle with this internal symmetry. It's like, no, we can just compute the S matrix in some more direct way. So in any case, that's a few thoughts about that. But I think the big challenge right now is to understand how to build this formalism, how to build infer geometry, how to build this kind of sub-Feynman diagram formalism and so on. And I think one of the features of these things is the realization that you have to have idealized observers in this picture to be able to build these things. That it doesn't work, that to go from just hypergraphs to something like geometry, you have to be making equivalence classes of things, which you do by saying, well, an observer can only detect these things in this equivalence class. They can't detect the individual elements of the equivalence class. And that becomes very important in being able to see how one emerges, how sort of a geometry-like thing emerges from that. But anyway, that's sort of the current state of those things.